Hello and welcome, class, to Chapter 10, Part 3 in Burge and Overby's 4th edition, Chemistry Atoms First. In today's lesson, we are going to be talking about the experimental measure of enthalpies and heat changes known as calorimetry. So as a brief reminder, we have talked about systems, surroundings, basic definitions, and thermodynamics, as well as in the previous lecture we introduced enthalpy, or delta H. Alright, so what we are picking up with today is heat capacity versus specific heat, how they are a defining characteristic of a particular material, and what they have to do with heat and enthalpy. Alright, so heat capacity, or capital C, is the variable that our textbook uses. If you're using a different textbook, it is actually very common that this variable here is not represented by a capital C or just a lowercase c. So if you took chemistry in high school, if you have a different textbook, if you're not in my class, be aware. This variable might be a different letter. It might be a different notation. If you're with me in the spring of 2021, heat capacity is a big ol' capital C. So be aware of that. What heat capacity represents is the amount of energy necessary to raise the temperature of your substance by a single degree. In other words, how hard do you have to work to change something's temperature? How much energy do you have to put in to change its temperature? Now, something that's really important about heat capacity in terms of its technical definition is that all of these values are measured at constant pressure. So also you can feel free to keep that in mind. All right, we can see the relationship of heat capacity, heat, and temperature in the equation below. Q is equal to capital C times delta T. Our Q is our heat. Our capital C obviously is heat capacity above. And our delta T is change in temperature. If we rearrange this equation, we can see the technical definition of heat capacity, not just the verbal definition above, right? C is equal to Q divided by delta T. Capital C is the amount of energy needed to raise the temperature of a substance by a single degree. So we're looking at heat per temperature change. Now, heat capacity is independent of the mass of the object. It's just dependent on the substance itself. So therefore, something like water, we know, takes a lot of effort. You have to put in a lot of heat to change its temperature. That's why you get the phrase, a watched pot never boils. Metals naturally have very low heat capacities, and substances like nonmetals have very high heat capacities. So a metal object, like a pan, you can set it on top of your stovetop, and you bet if your stove is hot, that metal pan is going to be hot pretty quickly. Non-metals, on the other hand, have very high heat capacities. They're very resistant to temperature change as a function of heat being added. So water takes a very long time to boil, right? A watched pot never boils. This is also why you use oven mitts to take a hot pan out from the interior of your oven. The pan is metal. It's going to be very hot, and it's going to transfer that heat to you pretty readily if you touch it directly. However, oven mitts are made of non-metallic components, right? It's like fibrous. It's made of cotton usually. Silicon is pretty common nowadays, but what they both have in common is that they're non-metals. Non-metals are not going to change temperature very readily when they get hot. Therefore, your hand on the inside of the mitt is going to be protected. Another really cool example of heat capacity and how it's dependent directly on the type of material is by observing what the two coolest states are. States meaning like states in the United States of America, not like state of existential being. And it's also important how we define the coolest states here. So we're not looking for states that have had like on record lows. What we're looking for here are states that have never broken 100 degrees Fahrenheit on record. Now, here's where normally in class we have a great conversation about, I have students guess, and, the most common guesses One is correct, the rest are not. The first guess is Alaska, and Alaska is one of those two states. In fact, it is Mount Denali that's pictured right here in Alaska. So if you're paying attention to the slide, you're like, oh, I know that that's probably a picture of Alaska. Alaska has never broken 100 degrees Fahrenheit. The second state is surprising. Again, the most common guesses after Alaska all tend to be incorrect. If you were to guess Minnesota, Maine, North Dakota, Wisconsin, some people even guess Michigan, and I'm like, have you lived here? Like, it definitely gets over 100 in some summer times. It's not super common because it's fairly temperate here due to the Great Lake effect, but like, you know, it still has broken 100 degrees. The other state that on record that has never broken 100 Fahrenheit is Hawaii. And the reason why circles back around to the fact that non-metals have high heat capacity. Hawaii is a collection of islands in the Pacific surrounded by water. And as the sun casts light down on the islands of Hawaii, the water that surrounds the islands actually absorbs most of the energy. And because water is very good at absorbing energy without changing temperature, the surrounding water of Hawaii helps to keep it a pretty temperate temperature, right? Like the fluctuation of the thermometer rarely changes there. It's somewhere between like 70 and like 80 pretty consistently throughout the year. So we can think of it almost as like the Great Lake effect that we experience here in Michigan, just on an even grander scale, because Hawaii is surrounded by nothing but deep ocean. All right, so let's contrast our definition of heat capacity with that of specific heat. Now again, the variable for specific heat might change all depending on what textbook you're using. In our textbook, specific heat is represented by a little s. Now, I actually prefer these variable definitions compared to other textbooks for one real big reason. Specific heat starts with an s, and it's being represented in our textbook by a variable s. To go backwards, heat capacity, which is represented by a capital C, is represented by a capital C because capacity starts with a C. Heat capacity and specific heat both contain the word heat, so it's very difficult to remember the variable if you're trying to think of heat. Instead, think of the other word that's present, C for capacity, S for specific. And the big difference between these two definitions, aside from what variable is used to represent them, is that specific heat pertains to mass, not just substance. Specific heat is the amount of energy necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius, again, at a constant pressure. The equation, as a result, looks a little bit different. We have Q for heat, we have S for specific heat, which is a constant, all depending on what type of substance we're working with, and our equation must also contain mass, right? Our specific heat is dependent not just on heat, not just on temperature change, but also on how much stuff we're working with. And of course, delta T is going to be change in temperature. Change in temp. The amount of energy necessary to raise the temperature of your substance, it would be the same if we're just looking at heat capacity, but it's going to be different if we are looking at specific heat. For example, let's say you wanted to heat up a 6-quart pot of water. You want to make some macaroni and cheese, right? You have some water inside of this container. You're going to have to put in a certain amount of heat to get this pot to raise from 20 degrees Celsius or room temp up to 100 degrees Celsius, which is boiling, and you can actually start making your food. The amount of heat required to perform this change is going to be less than that if you were trying to heat up, let's say, your bathtub with its little clawed feet to boiling. I don't know why you'd want to heat your bathtub up to boiling. That wouldn't be safe for human exposure. But the point is that this bathtub is going to contain way more water than that 6-quart pot. So if you want to bring this amount of water from 20 degrees to 100 degrees, yes, the substance might be the same, and its internal resistivity to change might be the same, but because we have more water, it's going to also take more heat to get the job done. So whether you are going to use your heat capacity equation, Q is equal to C delta T, or if you're going to use your specific heat equation, Q is equal to SM delta T, is going to depend on the type of problem you're trying to solve. If mass is involved, we're going to default onto using Q is equal to SM delta T, and this honestly is going to be the more common equation to use anyway if we're observing experimental conditions and calculating some types of like real heats. So let's look at an example. So let's talk about gallium. Gallium is actually a pretty cool substance because its melting point is less than that of the regular temperature of the human body, which means you can hold it in your hand, which is what is being shown here, and it will start to melt. It actually used to be a really common, like old-timey prank. I forget if it was Elizabethan England or Victorian England. I think it was Victorian England when this prank was really common. Because gallium is like so easy to melt, it would also be very easy to craft into the shape of a spoon. You would give it to your guest during tea time, and the spoon would melt in the tea. And it'd be like, haha, pranked you, your spoon's gone. If you've ever seen the book The Disappearing Spoon by Sam Keane, the title of the book comes from this like old prank. The tea would no longer be safe to consume, but relatively speaking, gallium is pretty non-toxic. You can hold it in your hand like this and you would be fine. You just have to wash your hands afterwards and it's all good. So let's see, how much heat must be put into a 2.5 gram lump of gallium in order to raise its temperature from room temp, 25.0 degrees Celsius, to its melting point, which is 29.9 degrees Celsius. We can also see here that the specific heat of gallium is given, which is equal to 0.372 joules per gram degree Celsius. So you guys know the equation. I'm gonna give you the chance to just like plug and calculate yourself, get some practice with this equation, feel it out, and then we're going to come back together after you unpause the video and compare our answers. All right, let's come back together. Let's crunch some numbers. We're looking for heat. Heat is always gonna be Q. Heat is Q. We are going to need to input some values here. We can see we're given a mass, which means we have to be working with Q is equal to SM delta T, so we actually have somewhere to plug this mass in. Another big clue that we're using Q is equal to SM delta T is that we're explicitly given an S. If we're given a capital C, then obviously we're going to be taking more of a heat capacity approach. All right, so Q is equal to SM delta T. We have an S, 0.372 joules per gram degree Celsius. We have a mass, 2.5 grams, and we have a change in temperature. Now, delta T, in much the same way we saw with our enthalpy of reaction in chapter 10, part 2, is always going to be final minus initial. So we're going to take our final temperature and subtract out our initial temperature, and this is always going to be delta T. Always, 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 final minus initial. All right, final minus initial gives you the net change from beginning to end, and so now that we have inserted that value into our equation here, we can just crunch the numbers and calculate what our heat is going to be. Since grams are going to cancel here, degrees Celsius will cancel here, we can also see that our answer is going to be in the unit of the joule. Now the reason why I want to emphasize that this is the unit of the joule is because of the magnitude of heat that we're going to calculate. The value of 4.56 joules is the amount of heat that would be necessary to get this gallium up from room temperature to its melting point. Now, when working with units of energy, our answers can be kind of abstract, like either they're very large numbers or very small numbers. It's kind of hard to wrap your head around exactly what it means. So let me give you this. 1 joule is approximately the amount of energy that it takes to push a tomato 1 meter. So if you put a tomato on a table and you push it 1 meter, that's approximately 1 joule of energy. So the amount of heat it takes to take gallium from room temp to its melting point is the equivalent of pushing a tomato back and forth 4 times. 4.5 times, really. But you get what I mean. It's a very small amount of energy. That's not a lot of effort. That's not a lot of heat that needs to be transferred from your hand into the gallium to get it to start to melt. So how does heat capacity and specific heat wrap back around and connect to enthalpies and everything that we've been talking about before with chemical reactions and stuff like that? Well, calorimetry is that answer. Calorimetry is the experimental method of measuring quantities of energy associated with chemical reactions and physical changes. In other words, calorimetry is the measure of energy, right? Calor, almost like the calorie. The root word meaning or coming from the same place, calor translates to energy. So we're literally just measuring energy in the study of calorimetry. When undergoing a calorimetric study, there are 2 big things that we're going to take advantage of. The first is the first law of thermodynamics. If we are working with a closed system, the amount of energy that is transferring from the system is going to be equal yet opposite to that of the surroundings. So if our reaction or our system, let's say, is here and it's housed inside of some type of encased surroundings, so we're separating some of the surroundings from the rest of the universe to actually give us a meaningful thing to measure. Systems on the inside, measurable surroundings are present on the outside. If heat is going from system to surroundings, we know that the system is losing a certain amount of heat, and this controlled section of the surroundings is gaining that amount of heat, and vice versa. So Q of system is always going to be equal to negative Q of surroundings when it comes to calorimetry. Now, based off of the equations that we have just learned, the biggest or most useful one being Q is equal to Sm delta T. If we substitute Q for Sm delta T, what this means is that the mass of our substance and the temperature change of our substance that we're observing, multiplied by its specific heat, is also going to be equal yet opposite to the same of the surroundings. So if we observe the surroundings, if we already know some stuff about the system, we can figure out the energy that is transferring between them. Right, so these equalities are also kind of like mix and matchable because Q is equal to Sm delta T. And as long as there's a negative sign out in front, we can also partner systems and surroundings together. And we're going to be seeing an example of this quantitatively in a little bit. But before we get to that, I want to turn our attention to the illustration on the right. So what this little, maybe unfancy doodad is known as a coffee cup calorimeter. It measures heat inside of coffee cups. The reason why we use coffee cups, it may not seem like very technologically advanced, but coffee cups, which are made of styrofoam, actually have really high heat capacities. They're very good at insulating. So the reaction mixture is going to be our system, right? The chemical reaction is always the system, and all of the rest of the blue in here is the water. And the water surrounding the reactants / the products is going to be the surroundings. Right, so let's say we're mixing together like HCl and NaOH. Well, we're taking 2 reactants that generally come in the form of an aqueous solution, and we're mixing them together. Acid and base are going to react. The water is kind of incidentally there. It's the environment with which the reaction is taking place. Therefore, the water is going to be measurable surroundings. The coffee cups are going to separate the water from the rest of the universe. So we actually have a section of the surroundings that is going to be meaningful to measure and observe. Our nested insulated coffee cups are the calorimeter itself. We also tend to have a lid on top, like another piece of styrofoam is super common, just to make sure that we are creating as closed of a system as we can. And that way, as the reaction is actually reacting, the water is going to be the only thing we need to observe. So let's say the reaction is exothermic, the water is going to be heating up because the water is the surroundings and it's going to be catching all of the excess heat coming off of the chemical reaction. Now, how we observe the enclosed surroundings is with a thermometer. So if we stick a thermometer inside of the coffee cup, we can see whether or not the temperature is going up or if the temperature is going down. What we are observing here is the temperature of the surroundings, right? The thermometer is also not a part of the chemical reaction. Thankfully, because if it was, that would mean that the thermometer is going to be slowly eaten away, and that's not something we want. Right, the thermometer, because it's not involved in the chemical reaction, is technically a part of the surroundings as well. And because the temperature is surrounded by predominantly water, another aspect of the surroundings, the temperature is going to be keeping track of how the surroundings are responding to the system. So we always directly observe the surroundings, and the surroundings can give us some information about the system. We just need to be smart about how we use the variables that we're observing in the equations that we've been seeing so far. All right, so let's work through, honestly, one of my favorite example problems of the entire fall-spring semester combination. I don't know why, I just find this type of problem very aesthetically pleasing. It's one of those types of problems where you're like, I didn't even realize that there was a problem to solve for here, but now that I know, I'm just gonna see it everywhere. Let's say you're hanging out and you're camping. You have a 17.2 gram empty aluminum can. We can see that the specific heat of aluminum is provided to us here. And you accidentally toss it into your bonfire. You know, it's sitting on the rim, you're done with it, it falls in, you're like, I don't really care that much, it's fine. It's left in the embers until it is heated to 350 degrees Celsius. You're like, oh, I want to recycle the can, but it's too hot to just put straight up in the recycling bin. It might catch some paper that's in there on fire, or if you threw it in the garbage, there's something flammable in there, I'm sure. So let's cool it down first. You take the can and you put it in 100 grams of water. Let's say you also, that water is just in a collection of 2 styrofoam cups. It's pretty common, right? 100 grams of water is, if you remember, approximately the size of a 100 milliliter beaker from lab. It's not that much water and would totally reasonably fit within 2 stacked coffee cups. The specific heat of water is also provided here. And the water was initially at room temperature, which here we'll say is 25.3 degrees Celsius. What's the final temperature of the can? Is it safe to throw away at that point, or do you have to let it cool down even more? All right, so we have a lot of information here and a couple of equations that we're going to need. So we're just gonna parse through the information, we're gonna organize it before we actually start crunching any numbers. First and foremost, observe that the specific heat of the aluminum is pretty significantly smaller when in comparison to that of water. Again, our aluminum is a metal, and metals have very low heat capacities, very low specific heats, compared to that of a non-metal. So we can see approximately what magnitudes constitute high and low specific heats here. All right, so we have a mass for the aluminum can, we have specific heat for aluminum can, we have an initial temperature for the aluminum can. So I'm just gonna gather all of that information up here on the left. Mass of aluminum is equal to 17.2 grams. We have specific heat of aluminum, which is 0.900 joules per gram degrees Celsius. And we have initial temperature of 350 degrees C. All right, we have a similar set of information, a collection of information for water. I'm gonna put that up here on the right. So mass of water is equal to 100 grams. We can see there's a dot here, meaning that we have 3 significant figures in our measurement for water. The specific heat for water is 4.184 joules per gram degree Celsius. And last but not least, we have an initial temperature for the water that is equal to 25.3 degrees C. Right, so now that we have collected everything pertaining to the aluminum and separated it from everything pertaining to the water, let's acknowledge what is the system, what is the surroundings. There may not be a chemical reaction here, but our system is still going to be the object that's of interest to us. The object of interest is the aluminum can, so we are going to say that this is the system. And all of the information pertaining to the aluminum can is that of the system. The water, which we put the can in after the fact, is going to be the surroundings. This is important because when it comes to Q of system equaling negative Q of surroundings, we need to make sure that the right pieces of information are going to be on the right side of our equation. Otherwise, the numbers, as we start algebraically moving around, it's not going to make much sense. All right, so Q of system is equal to negative Q of surroundings. And what we're going to do is take the information here that has been given to us and plug it into a SM delta T of system is equal to negative SM delta T of surroundings equivalent. We're also going to keep in mind that delta T is equal to TF minus TI. Have to keep this in mind because there is a negative sign involved in this equation. If we plug the wrong temperatures into the wrong place, we're not going to get the correct magnitude of our temperature. All right, so let's take the information now. We're just gonna plug it in. We have figured out what's going on what side. System is aluminum, surroundings is water, so we're just gonna start plugging numbers in. Specific heat of aluminum, 0.900 joules per gram degree C. Mass of aluminum, 17.2 grams. Delta T is going to be TF, since we're looking for final temperature of the can, minus 350 degrees C. Now, it would also be at this point that we would start picking up and observing the units, make sure everything is working together. It appears as though it is. We have grams, we have joules, we have degree C, and that is it. There's no other mass units and no other temperature units, so there's no conversions we need to do for this problem. All right, so we have a negative 4.184 joules per gram degree Celsius for the specific heat of our water, 100 grams for our mass. Do we have a TF? It doesn't appear as though we have a TF. How puzzling. And here's where it's important to remember what it is that we're studying here. What are we observing? Final temperatures occur when our systems and surroundings have come into what is known as thermodynamic equilibrium. That's how we know that the reaction or exchange of heat is finished. And what thermodynamic equilibrium means practically is that once the reaction is finished, once our temperatures, once our energies are stable, the temperatures are going to be the same. So the temperature between our system and the surroundings will be the same once the heat exchange is finished. In other words, the final temperature of the can is the final temperature of the water. They're going to be the same thing once the heat is done exchanging from the can to the water. So we're going to plug in the same TF for the water on the surrounding side because these two TFs are going to be equal to the same thing. The difference is our initial temperature. Our water had an initial temp 25.3 degrees C. All right, so remember, temps are the same. Once we have reached thermodynamic equilibrium, this is going to give us the final temperature of the system and the surroundings. It just so happens in this case that we care more about the perspective of the can, hence why we defined it as the system in the first place. All right, everything is plugged in though. We have one equation, we have one unknown, they're just kind of split between two different places. So what we're going to do is rearrange this algebraically so that we pull everything pertaining to TF on one side and all of the numbers onto the other. Right, so we have to think back to like, what is that, 11th grade algebra, algebra 2, whenever you guys have to take algebra 2 in high school. We're going to use all of those old skills. So I'm not going to show all of the work here. I'm going to show one step of the work as we start rearranging and solving for TF. As we pull everything that has TF onto one side of the equation, and I'm just going to draw it here on the left-hand side, there should be a point in your calculations where you have 433.88. If we're keeping track of units properly, like how we should, this value will have joules per degree Celsius on it, and this is where our TF is. And this is equal to a 1.60 times 10 to the 4 joules. So this is the second to last step of all of the algebraic manipulation. There are a couple of different ways you can approach it, algebraically speaking, that are all totally valid, so I don't want to spend a lot of my time on that. But if you are having issues with your algebra, please get some practice in. Either talk to the math department, get a math tutor, work through some problems online, or even just crack open your old algebra notebook to remember how to solve and rearrange for this type of problem. TF, in the end, is going to be equal to 36.9 degrees Celsius. We would find this after dividing each of these sides by 433.88. Our joules will cancel out. The only unit that's left is our degrees Celsius. All right, so our final temperature of 36.9 degrees Celsius answers the immediate question, what's the final temperature of the can? Conceptually, we were also concerned with cooling the can off enough to be able to throw it away safely. 36.9 degrees Celsius is just slightly warmer than the human body. So this is totally safe to pick up even with your own hands and just throw it away, recycle it, dispose of it properly. All right, and this brings us to the end of our discussion of heat capacity, specific heat, and calorimetry. So calorimetry is something that we are going to be getting some active practice with in the lab space. Again, combining it with some calculations of enthalpy. Since we're looking for Q's, we can connect the Q to the delta H from before. But I will leave that exercise for when we are actually in the lab space. If you are not in my class, hopefully you would also get to experience a similar type of lab working through coffee cup calorimetry by hand. All right, if you have any questions on the material from today, if you're in my class, please don't hesitate to email me, set up either an appointment for office hours or something like that. If you are not in my class and you have questions, feel free to leave them in the comments section down below. If you have any homework, please do your homework. And until next time, class is dismissed.